Okay, so we're going to take a look at reaction mechanisms. Now, this in inorganic chemistry, mechanism means something very different than in organic chemistry. What we mean by reaction mechanism is a series of steps in a chemical reaction. So some chemical reactions appear to take place by one step, but in fact they take place by several steps. Okay, so even though reactions appear to be simple, the equation doesn't really tell us how it takes place. Okay, here's an example. This top reaction here, overall, we have NO2 plus CO goes to NO plus CO2. Seems like a simple thing. These two molecules exchange an oxygen atom. But in fact, it's not that simple. Okay? What actually happens is two NO2 molecules get together and switch an oxygen atom, or one gives the oxygen atom to another one. You get NO3 and NO, and then the NO3 encounters a CO, and NO3 doesn't like the extra oxygen, so it gives it to the carbon dioxide and becomes CO2. You'll notice I've canceled out, I've crossed out one of the NO2s on each side and one of the NO3s on each side to get the overall equation above. Okay? How do we know that this reaction mechanism is the actual reaction mechanism? Well, we've detected the presence of NO3, for example, in a reaction vessel, and so that means that there had to be what's called an intermediate. Okay? And we'll come back to this example and take a look and see how this all works in just a minute. So first thing you need to understand is that NO3 in the previous example was an intermediate. It's formed and then consumed. So it's formed early and consumed later, and therefore it doesn't appear in the overall because it shows up on both sides. It's first a product and then it's a reactant later on in a later step. Okay. There also sometimes will be catalysts. Catalyst is something that speeds up a reaction. It's not in the overall reaction, doesn't contribute, it just speeds it up. And it would show in a mechanism as first being consumed, a reactant, but then being produced again at the end. And the important thing about catalysts is they don't get used up in what they do. Okay? So we want to talk about something called molecularity, and that's how you have to have particles colliding in order to produce a reaction, the number of species that have to collide. Okay, there's unimolecular, which is a step involving one species. So in other words, something decomposes to products. Bimolecular would mean two species colliding together to form some sort of reaction, and termolecular would be three species. An elementary step is a reaction whose rate law can be written just from knowing the molecularity. In other words, you don't have to do it experimentally. You can just sort of look at the molecularity of it. You can figure out is it unimolecular, bimolecular, or termolecular. Now here's the important thing about this. Elementary steps can only be a maximum of bimolecular collisions or unimolecular decompositions in order to be considered an elementary step. Okay? Because of what governs this, in order for two molecules to hit each other and undergo a reaction, not only do they have to have the right energy, but they also have to hit each other in just the right way. It's very unlikely that three molecules will be able to do that successfully with any frequency. So the best you can do for an elementary step, a reaction that happens in one step, is two molecules hitting each other forming a product by molecular collision, or one molecule splitting into multiple products, unimolecular decomposition. Okay? This is in your book. You can take a look at this, but this just sort of gives you an idea of what these would look like. Okay? We won't see any termolecular elementary steps because of the lack of frequency at which three particles can hit each other with just the right orientation and energy. So the most you're going to see are bimolecular collisions and unimolecular decompositions. Okay? So the mechanism gives you the elementary steps that add up to give the overall balanced equation. It has to agree experimentally with the experimentally determined rate law. It has to agree with it, and I'll show you what that means as we do an example. And finally, you have to know what the rate determining step is. Okay, one of the reaction steps in a mechanism is going to be much slower than everything else, and because it's slower, the other steps occur very, very quickly. The rate determining step does what it says it does. It determines the rate of reaction. Okay, and it can be assumed to be the entire rate law. All right, but we'll need to do some examples so that you can kind of understand how this all works. So we're going to start with NO2 plus CO goes to NO plus CO2. These are all in the gas phase. The experimentally observed rate for this is K times concentration of NO2 squared. So this is a second order reaction. It appears as though this is a bimolecular collision. A carbon monoxide molecule collides with an NO2 molecule just the right way with just the right energy, and an oxygen atom switches. Okay? But bimolecular collisions are first order, and this tells me otherwise. This is not a first order reaction. This means that it can't happen in one step. Okay? So I have to propose a mechanism, and there have been a couple of mechanisms proposed, but the one that I just showed you has the first step is two NO2 molecules colliding with each other to form an NO3 and an NO. And the second step is an NO3 colliding with a carbon monoxide molecule to form an NO2 and a CO2. Now this is measured as being a very slow step, and this is measured as being very fast. Okay? If I cancel out things that show up on both sides, I'll come back to my overall reaction when I add these back together. Okay? Now, because this first step is measured to be slow, then as fast as this one goes determines how fast the entire reaction goes. So in other words, think of it this way. We've got two NO2 molecules that need to collide with each other in just the right way with just the right energy in order to exchange an oxygen atom. Okay? That doesn't happen very often. NO3 doesn't want to form. NO2 and NO2 are pretty stable as is. It takes a lot of energy and a right collisions for this to happen. But once it does, the minute you produce this NO3, unstable NO3, and it comes in contact with a CO, this reaction is very fast. So it doesn't really matter what's happening down here. It just matters that this is what's taking us the most time for this entire reaction to occur, is waiting for these NO2s to encounter each other and do this. That means that the slow step up here is called the rate determining step, RDS, rate determining step. Okay? Now, if the rate determining step is what determines the entire rate law, then the rate determining step has to jive with our rate law for this reaction that we've experimentally observed, that we've done experiments and we've calculated this the way we learned how to do, right? Well, the 2 up here tells me that there are 2 molecules of NO2 colliding with each other. NO2 squared, there's my 2 NO2s. Nowhere in my rate law expression do I see an NO3, which tells me that the NO3 is not going to be part of my overall rate, nor do I see a CO anywhere in here, which means that it's 0 order with respect to CO. It doesn't matter how much concentration of CO you have. This second reaction isn't going to happen until you make the NO3. So it's the production of the NO3 that takes the time, and since it takes 2 molecules of NO2 to do that, that's what the 2 means up here. Now, does that mean we can write a rate law from a mechanism? Well, technically you could suggest a rate law from a mechanism, but usually mechanisms are used to prove whether or not rate laws are accurate or not. Okay, that's what they're for. Here's another example. 2NO plus Br2 goes to 2NOBr, all gases. The measured or experimentally determined rate law is rate is equal to K times concentration NO squared times concentration Br2. Now it looks as though there's a 2 there, there's a 2 in front of the NO, there's a 1 for the order of Br2, and there's a 1 in front of the Br2. Looks like that could be an elementary reaction, because elementary reactions, elementary steps, you can write a rate law directly from them. But this can't be an elementary step because it involves the collision of 3 particles. Exactly right, never happens. Okay? So we need a suggested mechanism for this. So here's a mechanism that was proposed for this particular reaction. NO plus Br2. Now this is a very interesting reaction. Okay? This is very fast, and it reaches equilibrium. Okay? Equilibrium. The second step is this NOBr2 reacting with another NO to produce 2 NOBr. And that's very slow. Okay? Now, again, if I cross out the things that show up on both sides, I've got my total reaction up there. Okay? So what's going on here? What does this double arrow mean, and what's going on fast equilibrium? What is all that? All right, what this means is that NO and Br2, we have an NO molecule and a Br2 molecule. If they hit exactly right, they produce this unstable NOBr2, which is produced early and consumed later. It's an intermediate. NOBr2, though, is so unstable that sometimes it goes back and forms these two again. And we only go to the second step if it happens to encounter another NO molecule. In that brief second, you get this reaction, okay, where it'll collide and it'll give one of its bromines over to this one, and you'll produce 2 NOBRs. But this reaction only happens if it encounters one of these NOBr2s that's really unstable and sometimes goes back to form the original reactants. This one eventually reaches equilibrium, meaning we're producing as much of this as we are going backwards. And when these are produced, they can react with NO to form NOBr. But that's a very slow step. Slow steps are the rate determining steps. This is the RDS. Now, if I look at just this step here, I've got NOBr2 and NO. I have no Br2 by itself, and yet my rate law requires Br2. Well, I've got Br2 up here. I've got NO and NO. I've got 2 NOs that haven't been canceled out, and a Br2. Well, that's what this says I need, 2 NOs and a Br2. So this means not only did I consider the rate determining step, but I also had to consider this fast equilibrium step. The rule is that in figuring out if your mechanism supports your rate law, you have to consider the rate determining step first, but if you have any fast equilibrium steps before it, you also have to consider them as part of the mechanism.